Good day, ladies and gentlemen. You are welcome to our lecture number 4 on Chen723, which is basic electronics. Today we'll be looking at audio power amplifiers and their classes. As we have seen from our previous lectures, the transistor is used as an amplifier. That is a device that will take a low input signal and produce a higher output signal, and it can be audio and it can be radio. So the audio power amplifiers, as we know, they are the devices that we use as public address systems in our places of worship and in our ceremonies. Now these audio power amplifiers are designed with the aim of delivering maximum undistorted power. That is, the waveform of the input should remain the same. The only thing that differs is what? The amplitude. And they are connected to resistance load. These resistance loads, they are nothing but the speakers, and they have low resistance. It is either 4 ohm, 8 ohm or 16 ohm. And as I have said, they are of different classes depending on how the transistor is conducting over the complete cycle of the signal. The classes are given here. We have class A, class B, class AB, and class C. So let's start with the first one, which is class A. In the class A power amplifier, the transistor is always on. It is operating throughout the 360 of a signal. That is, this is the half cycle and this is the other half, which will give us 360 degrees. So the transistor in class A is conducting always, and the collector current is on. It is non-zero for complete 100% of the cycle, which is 360. And for this reason, the efficiency of this kind of amplifier is very small, because the transistor is always consuming power energy. The second class is class B, and sometimes we call it push-pull amplifier or complementary symmetry amplifier. They are this type of amplifiers, that's class B. They are made using two transistors. One of the transistors will be amplifying the positive half of the signal, while the other one will be amplifying the negative half of the signal, which means the transistor number 1 will conduct for a half cycle, number 2 will now take over and conduct for the second cycle. Look at it. This half cycle, which is the positive, is taken care of by transistor number 1. Then the negative is taken care of by transistor number 2. So each transistor, as we have stated, is conducting for the half of a cycle, that is 180. And for this reason, we have advantage of higher efficiency, because the transistors are working only for 50% of the time, unlike the class A, where the transistor is always working. Now this class B amplifier, it has a problem. We call it crossover distortion, and these diagrams now will explain what crossover distortion is. This is the positive half cycle that will be taken care of by transistor number 1. This is the negative half cycle for transistor number 2. So ideally we need to combine the two to have a clear sine wave. But this position where they have been combined, you can see that there is a space where the signal is on the zero line, and this is what we call the crossover distortion. If we want to reduce this problem of crossover distortion, we have to make sure that the two transistors that we use, they are closely matched. That is, their properties are very much close to one another, and the amplification of each one of them is the same to the other. So if we do that, the problem of crossover distortion will be greatly minimized. And as we have already mentioned, the class B amplifier, it is made using two transistors. One is PNP and the other one is NPN transistor. And the load, that's the output, is from the common emitter of the two transistors. For us to understand this, look at the diagram. This is my transistor number 1, a PNP. This is my transistor number 2, NPN. And this is the emitter for the NPN, and this is the emitter for the PNP. And at their meeting point, we are now taking our output. And this output is being delivered through a capacitor C1 and then to the load resistance, which I told you is amplifier, which is the loudspeaker that has a resistance of either 4 or 8 or 16 ohm. Now the transistors, as I have already explained from the diagram, they are isolated with a capacitor. That's capacitor C1 we have seen. The single power supply is used for the two transistors. We don't have two power supplies for transistor number 1 and transistor number 2. No, this is our supply PCC, and it is common to all of the transistors. Now the capacitor is blocking the DC voltage, that is VCC square over 2. It is blocking it from the load. It don't allow the power supply voltage VCC, as we have seen from this diagram. It don't allow this VCC to go directly to the load. It is blocking it. And the function of the transistor, normally it is blocking the DC component of the signal. So it blocks it to Q2 when the Q1 is not conducting, and it will also block it for Q1 when the Q2 is not conducting. And the DC load line for this kind of amplifier is a vertical, because this transistor is acting as what? Open circuit for the DC. Whenever the DC signal comes, it will not allow it to pass. Then the current at the collector of the transistors is set to 0, because the class B amplifier, it is what? Blocking one of the transistors. When it is conducting, the other one will be off. This is what we have seen already. This is the amplifier. This is transistor number 1, this is transistor number 2. The first one, the arrow is pointing in, it is what? PNP. This one, the arrow is pointing out, it is what? NPN. And this is the waveform. In this half cycle, the positive transistor Q1 is conducting and Q2 is off. In the second half, the transistor Q2 is conducting and the Q1 is off. The impedance, input impedance to this circuit, that's the total resistance that the class B amplifier will see. Rin is equal to Rb in parallel to beta RL, where Rb is equivalent resistance between R1 and R2 for both transistors, and beta is the gain amplification of the amplifier, and the RL is the load resistance, which I said is the loudspeaker, which either 4 ohm, 8 ohm or 16 ohm. Now if you change this one, because these two lines, they mean they are in parallel, so I will say the product all over the sum, and we know this Rb is what? The parallel equivalent of R1 and R2. So the current gain of the push-pull amplifier, that is class B, that is AI is equal to beta times Rb all over Rb plus beta RL. And if you remove this Rb and put the parallel equivalent of R1 and R2, you finally get R2 all over R2 over beta plus 2RL. And the voltage gain, that is the VAV, is equal to current gain times this. And if you evaluate it, you finally get 1. That is, the voltage gain is equal to 1. The voltage output and the voltage input are the same. Now these are some of the important things we need to take note about this class B amplifier. The first one is, if we want to avoid the crossover distortion, the transistors R1 and R2, they will be replaced by a single variable resistor. That is a resistor that will be adjusted. You can either increase the value or reduce it by turning. And the value of this variable resistor must be bigger than 2 times R1. And that resistor is used for raising the collector current above 0. And if you do that, it will make the circuit to operate as class B operation. And also the capacitor C1 that I said is used for blocking the DC component and isolating the Q1, the transistor 1 and transistor 2. It is selected at lower frequency cutoff, and we use this relation to select it. The XC, which is the capacitive reactance, is equal to 1 over omega C1, where omega is 2 pi F, so that if we make C1 the subject, it is equal to 1 over 2 pi F XC, where F is the frequency and the XC is the capacitive reactance. Then that is all about class B. Then we go to class AB, and it is the one in which the transistor is conducting for more than 50% of the cycle. In class A, 100%, in class B, 50%, and here in class AB, it will be in between. That is more than 50% but less than 100%. And in this one, the distortion, the crossover distortion, is reduced. The efficiency of this amplifier, that is class AB, is also improved, since the conduction of the transistor is less than what? 100%. Though it is more than 50, but it is what? Less than 100% as in class A. So the class AB amplifier, it is also push-pull arrangement because it has two transistors. Transistors 1 and 2. While one is conducting, the other one is off. Then the next class is class C amplifier, and in this one the transistor is conducting only when the input signal is above certain positive value. That is, it doesn't have a fixed time of what conducting. Whenever the input signal is below that reference value, it will not conduct. But the moment it is above that reference value, the transistor will start to conduct. So in this case, the collector current of the transistor is non-zero for a less than 50% of the time. Remember, for the class A, 100%, class B, 50%, class C, more than 50 but less than 100. But in class C now, where it conducts only when the input is above certain positive value, the conduction time for the transistor is less than 50%. And this one is implemented using what we call the tune circuit. And this tune circuit consists of inductor and a capacitor, and it is used at the output of the transistors so that it will be at resonance. The function of this tune circuit is to filter harmonics. That is, any multiple of the original frequency will be blocked, will not be allowed to pass. And it has large amount of power output. And of course, this class C amplifier, we use it for transmitter output stage. That is, transmitters that are used in radio and television stations, they are employing the use of what? Class C amplifiers. Now, the power of class B amplifier. We are going to present some calculations here. The power from the source, that is our VCC, that we have seen previously, is now divided between two transistors, R1 and R2. As we have seen, each of the transistors has its own R1 and R2. This is R1 and R2 for this transistor, and this is R1 and R2 for this transistor. So the power from the source is divided between these two resistors, and part of the power to the transistor, it will go to the load directly. Then the remaining is now dissipated by the transistor. So the power input to this transistor in class B power amplifier is given by this. Power from the VCC, that's from the external supply, is equal to the VCC voltage plus what? The DC times DC current. But the value of this DC current is determined as IDC is equal to 1 over T, which is the period, integral of I of C1. This is integration. If you integrate it, you end up getting this. We are not going to be learning mathematics here. So the the value of this integrated signal is equal to 1 over phi times IC maximum. So if I take this one and replace it here, I will say my power is equal to VCC, which is here, times IDC, and the IDC is equal to a IC over what? Pi from this, where the IC is equal to VCC over 2 times RL, where RL is the what? Resistance of the load, which I said is the speaker. It can be 4 ohm, 8 ohm, or 16 ohm. So if we want to get the maximum power to be delivered to the transistors, the formula is this. That is, PVCC maximum is equal to VCC square all over 2 pi RL. And how do I do that? I remove this IC and replace it by what? VCC over 2R. So if you do that, you end up getting this formula. That's the power. Now, the maximum power from the transistor, that's the output power, is given by 1 over 2 IC square times RL. But the IC, as we have seen previously, is equal to VCC all over 2 RL. So now my output power maximum will be equal to 1 over 2 here. Instead of putting this IC square, I'll put VCC over 2R, all of them square, times RL. So if you do that, you get VCC square all over the square of 2 here should be 4 times this 2 will give me 8. Then this RL will cancel one of this. I will be left with 8 RL at the denominator. So if you want to get the efficiency, is the output power all over what? The input power times 100. This is my output power. And if I go back, this is my input power. This is my input power. So the efficiency should be equal to the output power all over the input power, all times 100%. And you can see that VCC square on the top will be cancelled by CC square on the bottom, and RL on top and RL on the bottom will be cancelled. So I will be left with 8 over 2 pi times 100%, which is equivalent to what? Pi over 4 times 100. And if you evaluate this, you know pi is 3.124142, and it will be given you 78.5, which is the efficiency of this class B amplifier. So the class B amplifier is more efficient than class A, because the class A, the transistor is always conducting. Now let us take a work example to see how we can use those formulas we have just finished discussion. The question says a complementary symmetry audio amplifier is designed with the power output of 0.5 watt and at the low frequency cutoff of 60 Hz. The loudspeaker is of resistance 8 ohm impedance and it is used, and the transistor's gain, that is the beta, is equal to 60. So if the power supply, that is our VCC, is 12 volt, we are now asked to determine the IC, that is the collector current maximum, the value of the capacitor C1, and the power supply to the circuit, which is VCC, and also to find the efficiency of the amplifier. Now this is our solution. The values that are given in this question are the load power, which is 0.5, the frequency, which is 60 Hz, the load resistance, which is 8 ohm, and the VCC, which is what? 12 ohm. Now if we want to find the IC current, we use this formula. The output, the power to the load is equal to 1 over 2 times IC square times RL. If you multiply both sides by 2, my IC square will be equal to 2 PL all over RL. That's, I make this IC the subject, because the question says I should find IC. So since this is square, I'll take the square root of both sides, so that my IC maximum is equal to square root of 2 PL all over RL. So I'll say 2, my power to the load is equal to 0.5, and my RL is the resistance of what? 8 ohm. So 2 times 0.5 all over 8, whatever I get, I'll take the square root, and this gives me 0.354 amp. That is my IC. That's the first part of the question. The next one, I am asked to find the capacitor C1, and I know the formula C1 is equal to 1 over 2 pi f xc. But this xc, that is the capacitive reactance, it must be equal to the RL if we want to get maximum power transfer. So the RL is already given as 8. So I'll now say my C1 is equal to 1 over 2 pi times f times xc. That is 1 over 2 pi. My f frequency is given as 60. And since we say this xc must be equal to RL, the RL is 8. So if you say 1 over this will give us approximately 332 microfarads as our value of the capacitor. Then the next question says we should find the power input, that's PVCC, and the formula is given here as we have derived it previously. VCC times IC maximum over 5. The VCC, the power supply voltage, is 12, and my IC max, I have just calculated it from here. Look at it. I have calculated the current from here. That's 0.354. So now I will say my IC is 0.354 all over pi. So just multiply 12 by this all over pi, which is 3.124, as we all know. You end up getting 1.35. This is our input power. So if we want to get the efficiency is equal to power output, that's power to the load, all over power input times 100. Power output is given in the question as 0.5 watt. The power input we just calculated as 1.35 here, then times 100. If you say this over this times 100, it will give you 37%. So you can see the efficiency is very low. It is even less than 50%. The last thing in this lecture is what we call a Darlington Pair circuit. The Darlington Pair circuit is nothing but a circuit consisting of two transistors. And as you can see from this diagram, this is transistor number 1 and this is transistor number 2. The collector of the first one is directly connected to the collector of the second. The emitter of the first one is connected to the base of the second one, and combined the two now, it is as if I have a transistor with the base here, with collector here and the emitter here, but actually it is two of them inside. So that is why we call it Darlington Pair. And as I've said, it is made by cascading two transistors, and the circuit, it have high input impedance and it has low output impedance, and it has what? High gain current. The overall current gain for this is the product of the gain of the first transistor and that of the second. That is to say, overall beta is equal to beta 1 times beta 2. That is that of number 1 and that of number 2. The disadvantage of this transistor is that it has high leakage current. That is, the no load current is very high, and it can be used for either common emitter circuit or common collector circuit, what we call emitter follower design. So ladies and gentlemen, this is the end of today's lecture. As I always say, for you to understand this better, you need to watch it many times, and definitely that will make it very simple for you. And I want to assure you that these lectures I've given you, they are exactly what I will be used for setting your exams, and if you watch it many times, it will make it easier for you to answer. Thank you very much.